Hey guys, in this video I'd like to finalize the Phong reflection model by adding the specular component to our lighting shader. As you recall, the specular component is what gives objects the shininess that we expect to see on various surfaces such as metals, marble, etc. In the previous tutorial we went over the diffuse component and we saw that the two main factors in it are the direction of the light and the surface or vertex normal. The reason is that diffuse lighting is based on Lambert's cosine law, which targets an ideal diffusely reflecting surface. This means that the reflected light is scattered all over the place in many angles, creating an equal light intensity for all the possible locations of the viewer. We calculate that intensity using the dot product between the light vector and the surface normal. In the real world we have, for all practical purposes, an infinite number of light rays that are bouncing back and forth between the Earth and the atmosphere, but when it comes to shininess in objects, the intuition is that there is a concentration of light rays that are reflected back from the object at a specific direction. And if a viewer is standing in the proximity of that direction vector, their perception of this concentration will be that the object is shining at them. This, my friends, is the specular effect. You can imagine that this reflecting vector is actually in the center of a cone, and whether or not the viewer will see the shininess depends on whether they are standing within that cone. If the viewer is outside of the cone, then they will only get the standard diffuse lighting effect. In the Phong reflection model, we can actually tune the width of the cone. A wider cone means a decreased effect of specular lighting, as the reflected light rays are spread out over a larger area. Therefore, a narrower cone means that more light rays are reflected on a smaller area, which should increase the specular effect. Now let's see how we can calculate the specular component of the Phong model. In the following diagram we have the reversed light vector L. We also have a normal denoted N, and for the simplicity of this demonstration I'm using standard surface normals. In the implementation, we will use the same vertex normals that we've been using for the diffuse component. By the way, make sure to watch the previous video if you're not familiar with the diffuse lighting, vertex normals, or any other concept that I've mentioned. You can find the link in the video description below. Okay, in addition to the reversed light direction, we have the location of the camera, which of course represents the eye of the viewer. An interesting side note is that we don't care about the direction of the camera because we assume that if the object is not located inside the view frustum, then it won't be rendered, so naturally we won't need to calculate any lighting effect on it. So we only care about the vector that goes from the pixel to the camera, which means we depend on the camera location and not its direction. Now let's reflect the light direction over the normal. It hits the surface at some angle, and it is reflected back at the same angle on the opposite side of the normal. The diagram is of course two-dimensional, but even in the actual 3D world this reflection is well defined because the light and the normal vector form a plane, so the reflection takes place on that plane. Okay, how about that? The camera happens to be located exactly on the path of the reflected light vector. As the camera moves away from the reflected light vector, the specular factor decreases. If you saw the previous tutorial on diffuse lighting, then it will not surprise you that we use the same dot product between the reflected light vector and the vector that goes from the pixel to the camera in order to calculate the specular factor. We will make sure that both vectors are normalized so that the dot product will yield the cosine of the angle between them. If the angle between the two vectors is equal or greater than 90 degrees, the result of the cosine will be equal or less than 0, and in that case we will disable the specular effect completely. Therefore, the relevant range of the cosine factor is between 0 and 1, same as diffuse lighting. But it doesn't end there. We want to enable the modeling artist to control the glossiness of the material. If the material is highly reflective, such as shiny marble, we want the cone of the light reflectance to be very narrow, and in this case the viewer will experience a high level of shininess and then a sharp fall off of the shininess as they move away from the center of the cone, and vice versa. If the material is more glossy, we want a gradual decrease of the shininess. An expert modeling artist will use this capability to mimic the behavior of common materials from the physical world to enhance the realism of the 3D scene. To do that, we add yet another control knob into the formula called the Phong exponent, or the specular exponent, or the specular power. We basically take the result of the dot product and we raise it to the power of this specular exponent. Since the valid range is between 0 and 1, the higher the specular exponent is, the more drastic fall off of the specular factor will be. The modeling software will use higher levels of specular exponent for shiny materials and lower values for more glossy ones. In terms of setting the specular exponent, there are at least two options. In many tutorials, and probably in actual implementations as well, the specular exponent will be set once for the entire mesh or a component of the mesh. This is simpler to implement and is perfectly fine. A more complex implementation calls for a texture map of specular exponents that provides you with the fine-grained control of the shininess, almost at the pixel level, depending of course on the resolution of the texture and the distance of the projected object from the camera. In this tutorial, I will show you the version with the texture map, and it should be very easy for you to replace the map with a single value. Here's an example of the texture with specular exponents that we will be using in this tutorial. The values represent grayscale, so the darker areas are lower exponent values, while the lighter ones are higher values. So the final equation for calculating the specular factor is a dot product of the reflected light vector with a vector that goes from the pixel to the camera, and the result of the dot product is raised to the power of the specular exponent, which can come from a texture or simply be a single value for the entire mesh, whatever you decide. This specular factor is then multiplied by the material specular color and the light color. In some resources, you will see separate light colors for diffuse and specular, but I decided to use the same one for simplicity. In the final lighting equation, we will add a diffuse color, which is calculated by multiplying the color of light by the diffuse intensity of the light, which is a single scalar value, and then by the diffuse color of the material, and finally by the diffuse factor, which is the dot product of the reverse light direction and the normal. Both vectors must of course be normalized. To the specular and diffuse colors, we add the ambient color, which is very similar to the diffuse color, just without the diffuse factor. We multiply the light color by the light ambient intensity, and then by the ambient color of the material. You will often see people clamping each channel after summing up the ambient, diffuse, and specular colors to a maximum of 1 to avoid a possible overflow in the combination of all these different components. After we do that, we multiply the result of the color, which is sampled from the texture, and this provides us with the final color of the pixel. Now, I want to let you in on a little secret with regard to reflecting the light vector over the normal. As you shall see, GLSL provides us with a very convenient internal function to get the reflected vector, but if you're familiar with my tutorials, then you know that I always want to make sure that I understand everything that is going on. So let's take a quick look at the actual math, okay? So here's the light vector L, the normal vector N, and we want to calculate R, which is the reflectance of L over N. First, let's reverse the light vector, and since vectors don't have a starting position, we can write it like that. Next, we want to project the light vector on the normal. The idea behind projecting one vector on another vector is to get the amount of the first vector that goes along the direction of the second vector. As you can see in the following example, with a vector 2 by 1, we can project it on the two major axes, and we get that it goes 2 units along the x-axis and 1 unit along the y-axis. This is a very trivial example, but it works well with any combination of two vectors. Surprise, surprise! The vector projection is also calculated using the dot product, which gives us the amount by which one vector goes along the direction of the second vector. Since the dot product results in a simple scalar value, we have to multiply it by one of the participating vectors to get the actual projection of the other vector on the first vector. In this case, we multiply the result of the dot product by the normal, so we get the projection of the light vector on the normal. We can now add the projected vector to the reversed light vector, and this brings us back to the line which serves as the surface of the object. If you don't understand why this is correct, simply notice that these two triangles are identical. We can now add the projected vector again, which brings us directly to the tip of the reflected light vector. Now let's rewrite this in a more common way, and we get that the reflected vector equals to twice the dot product of the light vector and the normal vector minus the light vector. Okay, so before we jump into the code, let's remember that for performance reasons, we do the diffuse lighting calculations in local space. Again, this was all discussed in the previous video. Naturally, we want to do the same with the specular component. We already have the light vector in local space from the diffuse lighting stuff, so all we need to do is bring the camera location from world space into local space. This will allow us to compute the vector that goes from the pixel to the camera in local space. In the following example, we have a representative transformation of the object from local to world space. Let's say that we scale up the size of the box a bit. For simplicity, we assume that we only do uniform scaling. Next, we rotate the box by 45 degrees counterclockwise, and finally, we translate it to location one by one. Let's assume that the camera is located in the world at 2 on the x-axis and 3 on the y-axis. So we get the following vector from the camera to the center of the side of the box. Obviously, this vector is going to be a bit different for each pixel, but we will use this one for this example. In order to get the camera from world to local space, we just need to backtrack what we just did. First, we need to apply the reverse translation on the camera location. So we add a vector -1 by -1 to the camera location at 2 by 3, and now the camera is temporarily located at 1 by 2. Notice that the box also has moved back to the origin. Next, we apply the reverse rotation on the camera, so we have to rotate it by 45 degrees clockwise. This brings the camera to about 2.12 on the x-axis and 0.71 on the y-axis. The box also rotates back to its original location. As you can see, the orientation between the camera and the object has been maintained as we moved from world space to local space. Since we limit ourselves to uniform scaling, we can actually skip the undo of scaling because it doesn't really affect the way that the object is oriented towards the camera. Okay, let's get on with the code review. Duke, take us there.
Come get some.
Let's begin with the material class. I've added the specular color, which we can find in the OBJ material format under the KS entry. I've also moved the texture from the BasicMesh class here because it makes more sense to keep all these variables together. So we have one texture which provides the base color of the object, and we have a new texture for the specular exponent. All this stuff is loaded in the BasicMesh class. I've done a bit of cleanup in the function init materials, so we have load textures and load colors. Load textures calls load diffuse texture and load specular texture, and in these functions you can basically find the same code that we had in init materials previously. In the case of the specular exponent, we just need to get the texture using a different SIMP macro, which is AI texture type _ shininess. There is a small caveat with the specular exponent texture, and that is that it's not RGB. So if you try to load it using our existing texture loading code, it will probably crash. Therefore, in the load function of the texture class, I've added a switch statement that handles 3 channels using the original code and 1 channel using GL_red in the internal format and format parameters. The function load colors simply loads the ambient, diffuse, and specular colors from the SMP material and stores it in our own material class. The final change in this file is in the render function, where in addition to the diffuse texture, we also bind the specular exponent texture map if it exists. I'm using the macro specular power unit, which is mapped to texture unit number 6. In general, this file helps me organize all the textures by allocating different texture units to different tasks, such as color, shadow, etc. That's it for the material and the BasicMesh classes. Next, let's take a look at the changes in LightingTechnique.h. First of all, you can see that I didn't add a specular intensity to the directional light, which derives from base light as we do with the ambient and diffuse lighting, because I felt that controlling the specular lighting through the material is enough. But it's all very flexible, so you can add and remove anything so that the model is right for your needs. But we do have a few changes in the LightingTechnique class. We have 3 uniform locations. One for the sampler, which will be used to sample from the specular exponent texture. Another uniform for the camera location in the local coordinate space. And finally, for the specular color in the material. We also have 2 functions to set the values into these new uniforms. The specular color is handled in the existing setMaterial function. The changes in the corresponding CPP file are also very straightforward. We need to get the location of the new uniforms and set their values into the shader. Now let's see the changes in the vertex shader, and this one is rather interesting. Usually we transform the position of the vertex from local space to clip space by multiplying it by the WVP matrix. So the original location doesn't reach the fragment shader, but we need the interpolated position in local space to calculate the vector from the pixel to the camera, so I've added a third output variable, which is used to pass the original position in local space, so we just need to copy the input into the output. Okay, cool. Now let's see the changes in the fragment shader. First, we have the new input attribute for the position in local space. We also have the specular color in the material, a sampler for the specular exponent map, and the location of the camera in local space. In the main function, I prepared a 0 vector for the specular color, and as you can see, we will do the calculation only in case the diffuse factor is positive, because if there is more than 90 degrees between the light vector and the vertex normal, then there isn't any diffuse lighting, so naturally there isn't any specular lighting as well. Inside this if statement, we subtract the local position of the pixel, which of course was interpolated by the rasterizer, from the camera location in local space. We normalize the result, and this gives us the vector that goes from the pixel to the camera. Next, we reflect the light vector over the normal using the internal GLSL reflect function, and we normalize the result as well. We do a dot product between these 2 vectors, and this gives us the specular factor. If the specular factor is greater than 0, it means that the angle between the 2 vectors is less than 90 degrees, so we continue. Otherwise, there is no specular effect. If the specular factor is indeed greater than 0, we continue and sample from the specular exponent texture. We use the special sampler for that, and we use the same texture coordinates that we use for the base color texture. We know that this texture has a single channel, so we add a .r at the end to extract the value from that channel. In GLSL, this is called swizzling, and you can do very cool tricks with it, like changing the order of the channels or duplicating a channel. In the future, we will probably find more opportunities to use this capability. So we sample the texel from the texture, and the value is a floating point between 0 and 1, so in order to translate it back to the actual exponent value, which was originally an unsigned byte, we multiply it by 255. So 0 is mapped to 0, 1 is mapped to 255, and everything else is just interpolated in between. Now that we have the specular exponent, we raise the specular factor to the power of this exponent using the internal function pow. To calculate the final specular color, we multiply the color of the light by the specular color of the material and also by the specular factor. Finally, we sum up the specular color with the diffuse and ambient colors, and after clamping, the result is multiplied by the base color from the texture to calculate the final color of the fragment. Let's take a look at the final set of changes in the main application code, and there are actually just two changes. One is very simple. We need to tell the fragment shader the index of the texture units used for the specular exponent. This part sometimes confuses people. When we activate a texture unit and we bind a texture to it, we use something like GL texture 0, GL texture 1, etc. This is an enum, which is defined by the OpenGL spec. But when we tell the fragment shader which texture unit to use, we use a simple index number. So for every texturing functionality, I have the texture unit and the texture unit index, but you need to remember when to use one or the other. To get the texture unit index into the shader, we use GL uniform 1i. The second change in the main application code is the transformation of the camera from world space to local space. We create a matrix for translating the camera to local space by calling getReverseTranslation on the world transform object. This function simply negates the position vector of the object and uses it to initialize a translation matrix. In the same manner, we create a reversed rotation matrix using the negative values of the rotations around the 3-axis. Next, we combine these two matrices to generate the final transformation. First the translation and then the rotation. Next, we extend the position of the camera in the world from a 3D vector to a 4D vector, and we make sure to place 1 in the W component so the translation will actually work. We transform this vector using the world to local matrix, and all that is left to do is to extract the 3D vector from the result and plug it into the shader. Of course, if you have multiple objects at different locations in the world, you will need to update the local position of the camera in this way before rendering each object. And here's the final result. If you enjoyed this video, please hit the like button and subscribe. You can also support this channel at patreon.com/OGLDEV. Thank you so much for watching, and I will see you on the next tutorial.